Welcome everyone to lesson 2.1 of Precalculus, where we're going to start to talk about arithmetic and geometric sequences. We are building into our exponential unit, and the way we're building to it is connecting linear to exponential, and we're doing that through the realm of sequences. So let's get started. So what is a sequence? This seems like it's been thrown at us from left field. We haven't heard this term before. Why are we using this as a bridge? Well, we have talked about sequences before. Any of you that had illustrative mathematics in Algebra 2, Unit 1 of Algebra 2 was actually all about sequences. You built equations for sequences based off of a recursive definition and then an explicit definition. We're not going to focus on the recursive here. We're just going to focus on the explicit, and we're going to use that as our bridge. So a sequence is just a list of numbers. They follow a pattern, and each number is a term. So the first number that shows up is the first term, so on and so forth. We use a different notation for sequences. We use this sub notation. You're usually used to a superscript where an exponent goes above and is a little bit smaller. We use a subscript for sequence notation, and we use it whenever we talk about different terms of a sequence. We'll use subscript instead of superscript. So we have S sub n, so not S of n, but S sub n, to represent the nth term of sequence S. And you can use whatever letter you want, just like functions. So we'll be changing that letter throughout, depending on what type of sequences we're talking about. But sequences are discrete points. Discrete mathematics is a whole branch of mathematics dealing with things that aren't continuous. These little individual things and how these individual things play with each other. So we're going to be using sets and things like that in order to describe distinct points instead of the interval notation that we have been using. So first type of sequence, because we're going to talk about two, is called an arithmetic sequence, or an arithmetic sequence if you so desire. So this is your linear-esque sequence. This is where you have a constant rate of change, so every term is related to the next through an addition of a number. So if I think about the sequence of 1, 2, 3, 4, the rate of change there would be a positive 1. If I think of a sequence of 7, 5, 3, 1, the common rate of change there, the constant rate of change there, would be negative 2. So it can be positive or negative, just like a slope. So arithmetic sequences have an explicit form, and there are a few different ways to describe it. So you have what is referred to as like the zeroth term explicit form. So if you have the zeroth term of a sequence, I'll tell you now, you very rarely ever have a zeroth term of a sequence, especially if it's defined as a list of numbers. You're always going to start at the first term. The only time where you might have a zeroth term is if it's defined graphically or numerically, but never as a list of numbers. So more commonly, you're going to see either the first term, so we'll call this the first term formula, or you could have the kth term. I apologize, my K's are awful. It's the worst letter for me. But if you have the zeroth term, you could also use this one. And this one is going to come up a bit next lesson, especially when we start to talk about the relationships between sequences and functions. That's going to come up a little bit. But if you notice, these kind of look like linear equations or forms of linear equations that we've talked about before. And this a sub n is just your nth term of sequence A. It's your f of x, essentially. And the d in all of these is your average rate of change, your slope, your m in a normal linear function. So we're going to write the explicit form of this sequence. We have 2, 5, 8, 11. And the dot, dot, dot just means it goes on forever. So it is an infinite sequence of distinct points. So what we need to do first is determine what the average rate of change is. Well, 2 to 5 is plus 3. 5 to 8 is plus 3. 8 to 11 is plus 3. So it seems like we're adding 3 each time. So plus 3 is going to be a rate of change. So how would I write this? Well, we could do the y equals mx plus b, but we'd have to find the b. And we can do that, and I'll show you how to do that a little bit later. But I'm going to use this zeroth term definition. So what I'm going to do is I'm going to say we have a sub n is equal to, the first term is 2 plus, and then we're going to do n minus 1 because it's the first term, and the common difference is 3, so we're going to multiply it by 3. So we have 2 plus n minus 1 times 3. So that's all fine and dandy. Maybe you don't like that. We can simplify this. We can distribute and then combine like terms. So we can say a sub n is equal to 2 plus 3n minus 3. So a sub n is equal to negative 1 plus 3n, which is perfectly fine. You can stop here. That is perfectly fine. Or you could stop here. Doesn't matter. It really doesn't. They're equivalent, and we got one from the other. The reason why the negative 1 makes sense is because that's the 0th term. If I follow the rate of change backwards one step, if I go from 2 and figure what happened right before it, well, that would have had to have been negative 1 to follow our plus 3 pattern. So both of those are fine. To find the 100th term of a sequence, you can pick whichever one you want. I'm going to use the one we simplified, and I'm going to say a sub 100 is equal to negative 1 plus 3 times 100. 3 times 100, 300, minus 1, a sub 100, or the 100th term, is 299. So not too bad. It would be awful to try to figure that out by hand, so that's why we can use these explicit definitions to help us out. Now we're going to do the same kind of thing again. We go from 7 to 2, 2 to negative 3 to negative 8, so on and so forth forever. It looks like to me 7 to 2 is minus 5, 2 to negative 3 minus 5, negative 3 to negative 8 minus 5. It seems like negative 5 is our rate of change. So we can do what I did before. A sub n is equal to 7 plus n minus 1 times negative 5. And I'm going to clean this up. I'm going to make it into that 0th term. So distribute, we get a sub n is equal to 7 plus, well, 7 minus 5n plus 5, because a negative times a negative is a positive. Combine the like terms, we get a sub n is equal to 12 minus 5n. So the 0th term is 12, and every time we're subtracting 5 from each and every term. The 50th term, well, a sub 50 is equal to 12, take away 5 times 50. 5 times 50 would be 250, so 12 take away 250, that would be negative 238. So a sub 50 is 238, not too bad, or negative 238. Not too bad. So that's arithmetic, that's linear-esque, right? The bridge here is what happens instead of adding by the same number each time, and you can add a negative, that's where that negative 5 comes from, adding negative 5 each time. What happens if we multiply by the same number? So whenever we have a sequence where we have a constant growth factor or common ratio, that's what we call geometric. It's the exponentials of sequences, essentially. And we have 3 forms that we can play around with for this one as well. We have a simpler form. We have the 0th term. We have the first term. And then we have the kth term. All of those are equivalent. They all mean the same thing. But in this case, instead of having addition to the same number, we're multiplying by the same number. So this r here in all of our formulas is that growth factor or common ratio, and the g sub 0 is the 0th term, g sub 1 is the first term, and g sub k is the kth term. So we're going to define this sequence in 3 different ways. So let's do the first term first, because that's the easiest. We're going to say g sub n is equal to, the first term is 2, times, well, we need to find that growth rate. 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54. So we're multiplying by 3 each time. So 2 times 3 to the power of n minus 1. And we can leave it like that. That's it. That's all we really need. For the 0th term, we have to figure out what happened before. Well, if we're multiplying by 3 to find the next term, to find the one before, we would have to divide. 2 divided by 3 is 2/3. So g sub n is equal to 2/3 of 3 to the power of n. You don't have to put the parentheses, but I do a lot just to differentiate things. When I have a fraction, it gets a little weird, so I'm trying to organize my work a little bit. The last one is the kth term, and it doesn't matter what we pick. For kicks and giggles, let's pick 54, just because it's large, it's weird, and it's perfectly fine to pick. So we're going to pick 54, and then we're going to do times 3 to the power of n, take away 1, 2, 3, 4. All of these are equivalent. They are all correct, and they are all useful in their own right. Now let's do one that's slightly different. Instead of growing, it's shrinking. So multiplication is the pattern. Well, when you multiply by a fraction, you can shrink it, right? Especially that fraction's between 0 and 1. Multiply by a half, for example, would make it smaller. So division is just multiplication by a number between 0 and 1. So division is perfectly okay. So if we look at our pattern here, we're going from 64, 16, 4, 1. A little hard to tell. 64 to 16, I can't. 4 to 1 is definitely divided by 4, though. 16 to 4, that's also divided by 4. 64 to 16, that's divided by 4. So we're dividing by 4, or you can think of that as we're multiplying by 1/4. So not too bad. So what is a common ratio? Well, the common ratio would be 1/4. You're always going to frame it as that multiplication. And if you want to show your work, or especially, it's a good habit to get into, you could do it's 64 divided by, no, you always do the second term first, Mr. Willie. It's 16 divided by 64. It's 4 divided by 16. It's 1 divided by 4. All of these are equivalent, but we're going to reduce a fraction as much as we can. So that's why we're going to stick with the 1/4 as our common ratio. Last but not least is, what's the explicit form of the sequence? Well, I'm going to do the first term because, well, I think it's the nicest. We have g sub n is equal to, well, the first term is 64. We're going to multiply that by 1/4 to the power of n minus 1. And that is it. So sequences, not too bad. Got to remember the distinct points. They're not continuous. They're not smooth. They're just little dots here, there, and everywhere that follow some sort of rule. We're only dealing with two types of rules. We're dealing with arithmetic, and we're dealing with geometric. We're dealing with addition and multiplication, and that's it. So hopefully this lesson wasn't too bad. If you have any questions about anything, please make sure you ask me in class. Otherwise, I'll see you in the next video.